All right, to start this video off, I wanted to spend a little bit of time talking about this new calculation technique that we're going to use for the remainder of the semester. It's called dimensional analysis. And it's kind of this big, intimidating sounding word. It's just a way for us to use a proportion in a certain way so that we can kind of cut out some of the individual steps. And then if we need to use multiple proportions, line up our work so that everything is nice and streamlined and we don't have to stop and start 2 or 3 or 4 times. Okay, so I mentioned that title because you'll see me use it in a couple of videos later on and in class. This is what I'm referring to when I say dimensional analysis. It's like a special type of calculation. Right? So if we go with something nice and simple, let's start with a dozen. I know that 1 dozen of anything is equal to 12. So this equation allows me to use a dozen over 12 as a proportion because I know, again, that the numerator and the denominator are the same. So 1 dozen is equal to 12. And then I can put in any number I want in either spot, and it allows me to convert the number of dozens to the number of total pieces, or the number of total pieces to how many dozens it's equivalent to. So if I have 3 dozen, I would then do 3 times 12. Let me put in my x. 3 times 12 is equal to 1 times x, and it allows me to use the proportion to figure out how many total pieces I have in this 3 dozen. Okay, so we cross the first, and then that's equal to the second cross. So 3 times 12 is equal to 1 times x. So 3 times 12 is equal to 36. And then technically, this 1, which I don't want to ignore, we would have to divide both sides by to cancel that out. Even though 1 times x is just x, bear with me for just a second. And then 36 divided by 1 is still equal to 36. So now x is equal to 36. Okay? Pretty straightforward. It's this multiplication and division from the cross multiplication that we want to take advantage of when we use dimensional analysis. Okay, so I'm going to keep this, but I want to start us off with how we're going to start setting up our work. And that's all going to be based on our starting value. So in the first example, we had 3 dozen as our starting point. And now instead of it being a proportion, and instead of the left side being equal to the right side, our starting value is already, we're going to multiply by what we call a conversion factor, or by a fraction. Okay, so if we start with dozen, what we want to do is multiply by a conversion factor, a fraction, where it's going to cancel dozen out and convert it to something else. So the base rule for dimensional analysis is whatever your starting label is, that goes in the denominator. Okay? And then just like we made sure the fraction of our proportion was equal to each other, because we know 1 dozen is equal to 12, we're going to make sure the fraction of our dimensional analysis is also equal to each other. So we know that there are 12 of something in 1 dozen. Okay? The purpose to this is that when you simplify this over, 3 dozen is going to multiply into the numerator of this fraction, and then the label dozen is going to cancel out diagonally. Okay, so ultimately what we wind up getting is 3 times 12 divided by that 1, which, remember the steps earlier, I said we did 3 times 12, and even though we didn't need to, we wind up dividing by 1, and so this equals the same answer, 36. Okay, so this kind of driven purpose of canceling things out so that their units will cancel out is the whole point to dimensional analysis. Okay? If we wanted to take it another step further, use a different example. Say I wanted to calculate, I don't know how many minutes old one of the students are in my class. Okay, so if we say that you are 16 years old, oops, get you on screen here. Let's say that you're 16 years old. Well, the first thing that I would want to convert to as we multiply, I know that in 1 year, it's 365 days. Okay, so in 1 year, it's 365. If I have 16 years, 16 times that number will tell me how many days old you are. So again, the function here is so that those units would cancel out. Then if we wanted to continue on to the number of minutes, we're going to multiply by another fraction. And the only label that I have left is days. So I'm going to put days down here in the denominator. And I know that in 1 day, we have 24 hours. And then again, all of these things are going to multiply across. So days would be in the numerator and the denominator, and they would cancel out. And then in the last conversion, I know, because I can multiply again, that in 1 hour, that's equivalent to 60 minutes. So now hours would cancel out. And instead of doing 1, 2, 3 individual proportions where we have this fraction equal to 16 years over X days, and then that number of days set up to that proportion, and then that number of hours set up to that proportion, we have 3 conversions lined up simultaneously. And so we'll eventually be getting to where some of our work looks like this, where we've got multiple fractions lined up. So we will have plenty of practice as we go forward. And just in case you're curious, as we crunch the numbers, if we've got 16 years times 365 times 24 times 60, you'd wind up equaling 8,409,600 minutes old. 409,600 minutes old. Okay, so you're not so young after all. You're 8,409 minutes, 600 minutes old. All right, for today's video, we are going to talk about this concept called the mole. We've mentioned it before, kind of talked about how big a number it truly represents. So we're going to break down really what the term mole ultimately means and how we use that going forward in chemistry. So in English, there's some words that always kind of evoke a certain number. We refer to those as counters. And so actually, we're going to take this over. So in this video, we're going to talk about the mole. And we've mentioned moles before. We had Mole Day last semester. And really, I like to break down just what the mole represents, just to kind of give a little bit more understanding as to why we use it, instead of just saying, yeah, it's a number, here we go. And so we're going to start with just identifying some of these terms that we refer to as counters. And a counter is just a word that always evokes a certain number. And so anytime you've heard of somebody refer to like a pair of shoes, you know that the term pair is always connected to the number 2, and that a dozen always refers to 12. If you're savvy enough, you know that a ream of paper is always equivalent to 500 sheets of paper. And then there's 2 ones that I just think are kind of fun to toss out there. If you've ever told somebody to just wait a moment or chill a moment, the actual standard length of time for a moment is 90 seconds. So anytime you've been told to wait a moment, you have to officially wait a minute and a half. The last one I think is kind of interesting. It has to do with this gentleman here in this picture who's laying on the ground. His last name is Smoot. And this is actually something that has taken place at MIT for the past several decades as like a tradition. Wouldn't know it, but these guys are in a fraternity, and they're at MIT again, so you can assume what the parties are like at the fraternities at MIT. But they decided to, I guess, pull some kind of like a prank, and they wanted to see how many body lengths it would take for this guy to measure across this really long bridge that spans MIT's campus. And so they picked him up by his wrists and ankles every single time, and they counted out, this is number 69. So they've already gotten that many body lengths, and they're still going. And so they've done this so much as a tradition at MIT that a smoot is an actual officially recognized unit of length. And a smoot refers to anything that is 5 feet 6 inches long, because that's how tall this gentleman was. And so if you go to Google and say 20 feet converted to smoots, it will convert any number of lengths you have into how many smoots long it is. Now, this has nothing to do with chemistry. This is not going to show up on a test. It's just something kind of interesting. But I like to kind of debunk the idea that these words always connect to a certain number. And so in chemistry, the unit or the counter that we use is a mole. A mole always just refers to a number. That's it. A mole of an element will have the same number associated with that depending on, or no matter what element you're referring to. Okay, so there's actually a number that's connected to a mole. We've seen this before. It's 6.02 times 10 to the 23rd power. All right, and it's a ridiculously large number because we've got 10 times itself 23 times. So we're talking something that's in like 600 sextillions. And there was an Italian chemist whose last name was Avogadro, and his work led us to understanding this number connected to the mole, so we refer to that as Avogadro's number. Okay? So if I had Avogadro's number of popcorn kernels and I spread that out over the surface of the Earth, how deep would that many popcorn kernels cover the entirety of the planet Earth? Okay, again, that number, 600, so write the number 602 and then write 21 zeros after it. That many popcorn kernels. Popcorn kernels are kind of small, but when you get to things that are in the 10 to the 23rd numbers, that layer of popcorn kernels would wind up being 9 miles deep. So tall would the Earth be covered in popcorn kernels that we would not even be able to see over the top of it. Okay, so this number is gigantic, right? And that's the number of individual atoms that we're going to need grouped together for the kinds of problems in the labs that we're going to be doing throughout the second semester. Seems like a lot, but when we start scaling things down to be smaller than a popcorn kernel, like an atom of hydrogen or an atom of carbon, that actually doesn't seem to be that big of a number. Okay, so we're going to do a little bit of math. We've already practiced a little bit of dimensional analysis at the beginning of this video. And so I really just want to reiterate that anytime we have two values that are equal to each other, so 1 mole, and there's our abbreviation for mole, not much of one, but it's just MOL. 1 mole is equal to Avogadro's number of particles. We can use this equation and set up two fractions. Okay, so these two fractions, the top is equal to the bottom, and here the bottom is equal to the top. So both of these fractions equal 1. Just 1. Okay, so anytime we have a fraction like this that represents the value of 1, we can use that to convert molecules to moles or moles to particles or molecules or anything like that. Okay, so I did want to talk a little bit about that. The term particle is kind of generic. Every year I say it's kind of like when if you refer to like a bumblebee as a bug is kind of a generic term. There's a lot of different things that make up the insect, group. So particles can be representing anything like atoms, or we can also say that they could represent molecules. Okay. So that term particle is just referring to something that's really small or really tiny. Right? So if we do these practice problems over here, it says how many molecules of copper 2 oxide are present in 4.5 moles of copper 2 oxide. 4.5, and then we abbreviate moles as MOL as our starting point. And again, this dimensional analysis that we're going to be using is driven entirely by the labels that we start with. So if our first number is in moles, then we're going to put the label mole in the denominator. And the goal is to convert it to molecules, and we have something that equates moles to molecules because you can remember that particles can also be referred to as molecules. So then which fraction would we use? Well, moles is in the bottom here. We want moles in the bottom in our work. So we're going to use these values. So we're going to say 1 mole in the denominator is equal to 6.02 times 10 to the 23rd. And that's where we're going to write the abbreviation for molecule is just MOLEC. Okay, so again, the work is set up in such a way that mole is going to multiply over into this numerator, and the same label is in the denominator. So these things are going to wind up canceling themselves out. And so 4.5 times Avogadro's number in the numerator divided by 1 in the denominator will give us our final answer. Okay? So I want you to pause the video, crunch the numbers. You'll need to actually get out your calculator. We're going to run through how we're going to set it up in the calculator because I want us to get comfortable using the buttons as we get ready to go into some of these things that require some scientific notation. All right, so you should have paused the video. Hopefully you're practicing this as you're watching it on your own. I want you to locate one button for me on your calculator, and it's right there next to the comma if you've got a graphing calculator. And on scientific notation or scientific calculators, the non-graphing ones, sometimes it's right by the 7 key, right? That button underneath the comma, it's 2 capital E's, and that stands for exponential notation. So when we want to write the number 6.02 times 10 to the 23rd, what we're going to do, let me try and fit this on the screen here, is we're going to type in 6.02, and then on the screen, we're going to hit second EE, and we get a little capital E to show up. And then we don't have to type in the time sign or the 10. That E stands for what would the exponent be on that 10. So we just do 23. Okay, so that's our way of getting Avogadro's number into the calculator. Now, when we actually get ready to run this, like actually multiply to get our final answer, one thing I'm going to encourage that you do is when you get ready to multiply or divide by Avogadro's number, or multiply or divide by a number that's in scientific notation, I want you to put that whole thing in parentheses. So we're going to do 6.02 EE 23. Okay. Usually when you're multiplying, there's no errors involved, but when you get ready to divide by Avogadro's number, without parentheses, your numbers are sometimes way off, and you get like times 10 to the 44th. And I don't want you to get any wrong answers, even though your work is set up correctly. So we're going to hit enter, and then we got to watch, because now we're looking at answers that are going to be these really large scales. We got to look for that E in our final answer. So it's not the answer 2.7. It's actually 2.7, and then the E stands for times 10. So it's 2.7 times 10, and then it was E24. So 2.7 times 10 to the 24th molecules. Okay. So in the second example problem, we're now starting with a certain number of particles. So we've got 4.5 times 10 to the 22nd, and then the abbreviation for particles can be just part. And again, our whole work, our whole purpose here is driven by that label. So particles is going to go in the denominator. And again, we've got that function or that equation that says this number of particles is equal to 1 mole. So we're going to use this fraction because it has that number of particles in the denominator. We're going to put 6.02 times 10 to the 23rd particles is equal to 1 mole. And as long as the numerator and the denominator are equal, we can multiply this number by 1, and we're just converting it to a different value. Okay, so again, all of these are going to be multiplied, but this time we would multiply this number into the numerator. So this times 1 is itself, but particles will be both in the numerator and the denominator. So we need to get in the habit of canceling out those labels. They're not going to be part of our answer anymore. And it winds up being 4.5 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. Okay? So again, pause the video, and then we'll run through how we're going to crunch the numbers in our calculator. Okay, so we're going to line up this so we can see it a little bit better. We've got our starting number, open parentheses, 4.5 EE 22. So that looks like 4.5 times 10 to the 22nd. And then we can multiply by 1, but any number multiplied by 1 is itself. So we're going to skip that step and then divide by the denominator. So divide, and then another open parentheses, 6.02 times 10 to the 23rd. Close, hit enter, and we get our final answer, 0.0747. So we're going to round that and say 0.075. MOL label, because that's the only label that's left from our work. Okay? So if we think about this for just a second, we know 1 mole is 6 times 10 to the 23rd. So in this question, we started with 4 moles. So we wind up having a greater number of molecules. 1 mole is 6 times 10 to the 23rd, so 4 of them would be 4 times that amount. So we've got times 10 to the 24th. Down here, we need 6.02 times 10 to the 23rd particles to even come close to having 1 mole. Again, that's our equation. We don't have that. We only have times 10 to the 22nd. So if we have less than the required number of moles, in our starting value here, this is not equal to 1 mole, so our final answer shouldn't be greater than 1 mole. So just taking a little bit of time to think through, like, should my number be really gigantic? Should my number be a decimal? Sometimes pays out in the end so that you get a little bit more confidence when you get numbers like this, and especially when you get numbers like this for a final answer.